Hey, thanks for tuning in for Lab 2, Motion of a Falling Object. I'm... shit. What's my name again?
Alex.
Alright. Alex Plager. So, to start this, I'd like to go over the main physics ideas. We're going to be having movement along one axis, and two forces are going to be present for this, gravity and air drag. The force of gravity is going to be calculated by 9.8 times the mass of our soccer ball, which is 0.45 kilograms, and you can see the calculation here. And the force of drag is going to be calculated as a proportion to the speed of the ball squared. In order to do this, we're going to be using Newton's second law again, that being F equals ma, and the momentum equation being final velocity is equal to the rest you see here. And our initial velocity for this ball is going to be 0 meters per second.
The video here is the one we're going to analyze for a tracker video and evaluate the motion of. Now it's a short video, so let's see it again. So, as you can see, the ball falls from a height and hits the floor and it bounces. Unfortunately, the video was formed in portrait, so it's appearing here in Windows Media Player in a landscape rotated 90 degrees format. However, for evaluation, we'll rotate the video 90 degrees in Tracker so that it falls along the y-axis. Or, even if we desired, we could just rotate the axis 90 degrees so that even though the ball is falling from left to right across the screen, it would still be tracked along the y-axis. Here in Paint is an incredibly detailed illustration of a model of the ball falling through the air. There are two forces acting upon the ball in the video, those being the force of gravity and the force of air drag on the ball. Now, we're going to create two separate models for this, one ignoring the drag on the ball and another incorporating the drag on the ball. So, these two forces, gravity and drag, are going to be facing in opposite directions, and the addition of the two forces will yield our net force. What that means is, once we add the two forces, if gravity is stronger than drag, then the ball will fall, and if drag is equal to gravity, the ball will reach what is called terminal velocity. However, we'll see that the ball is not falling nearly long enough in order to achieve terminal velocity. Here's Tracker with our video rotated 90 degrees, as we mentioned we would do earlier. This provides the picture in a sensical orientation in order to track the ball along the y-axis without too much rotation of the axes. You'll see that there's a slight rotation due to the angle the camera was held at. However, without further ado, here's the video in Tracker. So, you'll see that the ball appears quite blurry, and that's probably due to the subpar lighting in the room. Unfortunately, there's nothing we can do about that now. However, what you can notice is that the spacing between individual track points on the ball eventually spread out as it falls, suggesting that the velocity of the ball is increasing over time, implying that there's a net force on the ball. Now, this graph over here is rather nonsensical because it's displaying the x values over time, which don't really have much meaning. They're due to just sporadic variation of the accuracy of clicking on the mouse over time. So what we do want to pay attention to are these highlighted values right here, which give the y position of the ball, the position along the y-axis, as a function of time between 0 and 0.608 seconds, which is the amount of time the ball's been falling in the air. And our distance scale was measured using the diameter of the ball, which is 22 centimeters, as is typical of a size 5 soccer ball. Now that we've acquired the data for our experimental model position, we need to acquire our data for our computer model position. So, the data we need to input is the mass of the ball, which is easily available on the internet. The mass of a size 5 soccer ball is 0.45 kilograms. The gravity constant, 9.8 meters per second squared. Again, information easily available and needed to be set. And on the left side, our computer model is going to be ignoring drag, so we set the constant for drag to 0. So, our calculations for our net force are here, being the weight force of the ball is equal to mass times the acceleration of gravity times the j-hat direction vector. And our force of drag will be 0 since b is 0, and our F net will just effectively be our weight force. And Newton's second law is seen here because the change in velocity is equal to initial times the change in velocity. Same goes for the position of the ball. And so we just run our program and we get our results. And over here on the right side, we see our computer model that does involve drag. So we do set our proportionality constant to a value. And then we also calculated here being a value proportional to the square of the speed of the ball. and that'll yield us a different computer model. Live like your data, and when you're all set, you've got this graph right here. So this is a graph depicting our position over time, position versus time of our falling ball. It shows the comparison between our experimental position of the ball, depicted by the red line, and the orange and blue dotted lines represent the predicted position of our ball by our computer program. You'll see that our program that we wrote overpredicts the motion of the ball in time, and that's likely explained by the inaccuracies of pinpointing the location of the ball in the tracker video due to its blurriness and human error. However, our data does fit our model because they both display parabolic tendencies, which is to be expected of an object falling or an object experiencing negative acceleration. So, to answer our what if question of the week, what if our object was thrown downward? Would its terminal velocity change? The terminal velocity of the ball would not change, as terminal velocity is a function of drag in comparison to gravity force. Once the drag reaches equal in magnitude to the gravity force, the ball will stop accelerating and terminal velocity will be reached. And what does velocity over time mean in this context? Well, for the computation including drag, that ball will have a lower velocity over time and will also reach a terminal velocity because the drag at some point will reach the gravity force. And for our computer model without drag, the ball will never reach terminal velocity because there will be no drag to slow it down, and so the ball will keep falling and accelerating towards infinity speed.